nanohub.org.
Online simulation and more for nanotechnology.
Let's get started. So the first serious lecture, how to quantify uncertainties in physical models. And the basic things that I want to go over is basically to tell you what uncertainty quantification is and what is its scope and how it differs from machine learning and statistics, basically. Is there any difference? To learn to distinguish between two types of uncertainties, aleatoric and epistemic uncertainties, and then actually tell you that it doesn't really matter. To introduce the uncertainty propagation problem and the model calibration problem, just wave my hands and show you how these problems look like. And then we're going to have a hands-on example based on a catalysis problem. We're going to get experimental data and we're going to try to fit a dynamical system to that experimental data and study the sensitivity of the parameters we find, the sensitivity on the model outcomes based on the uncertainty we have on the parameters that we find. And this calibration, we're going to do it by hand. So we're going to do it by intuition, okay? All right, so what is the uncertainty quantification and why it's needed? According to Wikipedia, it's the science of quantitative characterization and reduction of uncertainties. It's pretty much what it is, okay? So it's basically talking about stuff that you don't know. That could be because that stuff is random or because you just don't know what they are, okay? This sounds like like statistics, but it's not really statistics or machine learning, because statistics just uses data to talk about things. We're going to use data and physical knowledge. All right, so uncertainty quantification would be basically the coupling of physics and data. Okay, so it's not, in statistics, you just make up models. You say, okay, let me assume a linear relation between this and that. Or let me assume a nonlinear relation of this form. We're going to say, well, we know a lot about what is actually going on. We know cause and effect relations. We know physical symmetries. Let's take that into account. Okay? And it's basically applied math. All right, so it's taking the physics, taking the data, and coming up with mathematical techniques to combine the two. All right, and things that we're going to be using are, of course, physical laws like partial differential equations, invariances, symmetries, and all that. Of course, the oldest example, I'm not sure if it's the oldest, but one of the most important examples of uncertainty quantification, successful application of combination of physics and probability or statistics is statistical mechanics. As you will gradually see, as we go through the class, successful uncertainty quantification techniques are not black boxes. It's not just you feed X and Y and you get an answer and you can do anything. It doesn't work like that. It works like that when your problems are very simple, when you have low dimensions, when you can query your information sources many, many times, then it works like that. It's just statistics. But if you look at real applications where you have constraints on how much you can run your computer, or run a simulation on your computer, or how many experiments you can do, or the number of variables you have is large, and by large I mean probably more than 5, then standard techniques do not work and you need to think about it. Okay, and you need to give it something, and that something is the physics. And that's why we spend 10 lectures on the language, because the most important thing is being able to state in the same language the physical assumptions and the statistical connections. All right, so let me give you some examples. This is an example from structure reliability. So you have here a building, and you can model the dynamics of this building. I mean, you can have a truss model of the building, and you can model its dynamics basically by Newton's laws. And you can have a dynamical system that describes the vibration of this building as it is excited, let's say, by an earthquake. Okay, so the earthquake shakes the ground, and the building is shaking, and you can actually solve Newton's equations and come up with the motion of its degree of freedom of the building. Okay? Now, of course, you know that if it shakes too much, if, for example, the maximum drift between two floors in the building exceeds a certain amount, let's say 2%, I don't know, that's probably too much, okay? You know there's going to be something bad happening. So, you may be interested in the probability that, you know, given the magnitude of an earthquake, the response of the building exceeds a certain limit state. Like the max of the drift exceeding, let's say 1%. And you can run simulations and repeatedly, and this is something that we're going to see how to do, and come up with a probability of failure, or otherwise known as the fragility curve. So given the magnitude of the earthquake, what is the probability that there's going to be something bad happening in your building? Of course, you're interested in that during the design phase, but you're interested in that if you are, for example, a city official and you have a bunch of buildings, you are in Los Angeles, let's say, and you would like to have the fragility curve for each one of your buildings so that you know that if something happens, you know, what is the probability that you have a significant damage and in which region and how should you deploy your resources to respond to that damage. These are open problems, by the way. We don't really know how to do that. So in the previous example, the uncertainty was basically in what exactly the earthquake does, which is not really something random. It is basically our lack of knowledge about the internal structure of the Earth. Okay, so let me show you another example. It has to do with the internal structure of the Earth. So an oil reservoir is basically a formation of rocks with a lot of basically it's a formation of a porous rock, and inside the pores of the rock there is oil. Okay. So during the first phase of oil production, you find a reservoir, you drill a hole, and because everything is under pressure, you're going to have oil coming out of the reservoir naturally, okay, until the internal pressure becomes the same as the external pressure. Now, this will give you like 30% of the oil, maybe even less. Then what you can do to get the rest of the oil out is you drill another hole and you pump water through that hole, and that water pushes the oil out of the first hole. Okay? And of course, you would like to optimize the location, let's say, of your drilling. So if you have an oil reservoir, you can pick the location of your wells, you can pick which wells are going to be injection wells and which wells are going to be production wells. You choose all that, you choose the location. And if you have a model of the porosity and the permeability of the rock, then you can infer how much oil you're going to produce as a function of time. And of course, you want to select the location of the wells so that you maximize that production. Okay? Now, the problem is that you don't really know how this looks like. You don't really know how the ground looks like. Of course, you can drill, take it out and look at it, right? But you cannot do that everywhere, obviously. The other thing that you can do is you can hit it and listen and have sensors that measure basically the response of that sound wave through the ground and try to infer the velocity of sound, the speed of sound inside the ground, and from that come up with the permeability. So you can solve an inverse problem to come up with how it looks like, but you can never really nail it. You're always going to be uncertain about what it is. Okay, so here's another example. This is an example of weather prediction. So if you want to predict, you see the video? Yes. So if you want to predict, let's say, the path of a hurricane, you really need to predict what the weather variables are going to do, like the temperature, the pressure, wind velocity, and all that. Okay, but these, and we have a pretty good idea about the equations that govern these variables, the Navier-Stokes equations, plus some thermodynamic assumptions. But there's a problem, and the problem is that even though you know the equations, I mean, you don't know all of them, but you know enough to get you started, you need initial conditions to start these equations. So these are partial differential equations that couple together the temperature field and the pressure field and the width velocity fields. Okay? So everything is a function of space and time, and to get started you need to know the initial temperature and the initial pressure, the temperature and the pressure now. Alright, of course you can measure them, you can have a weather station at many different points that measures these variables at that particular location, but to get started you need to measure them everywhere on Earth. So you cannot have weather stations everywhere, okay? As a matter of fact, most of your weather stations are in North America, okay? So that's one problem. You cannot know the initial conditions everywhere. Of course, you're going to tell me, well, I can have satellite images and I can gather the data from there. And that's great, but this is also not everywhere. This is at the very best at a resolution of 4 by 4 kilometers. Okay? Which is reasonable, okay? But it's still not everywhere and it's not 100% accurate. So you're gonna have uncertainty in your initial conditions. Okay? And that uncertainty, you will have to propagate it through your numerical weather prediction models, which are the partial differential equation models, as you solve them. And, every once in a while you're gonna have more data that you can incorporate, but you will always have a little bit of uncertainty. Now, on top of this uncertainty in the initial conditions, you're gonna have uncertainty because of the finite discretization of your equations. So, these are partial differential equations. You're gonna have to use some kind of finite volume scheme or finite difference scheme to solve them. And your grid, can you really make it, smaller than 4 or 5 kilometers? That would be ridiculous. Okay, we cannot solve this problem. So there's going to be also this kind of uncertainty. And that's why you cannot really predict what the path of a hurricane is going to be. So it's two things. Uncertainty about the initial conditions, but it's also discretization uncertainty. And that discretization uncertainty has to do with turbulence and our inability to predict it. But you can have a pretty good idea about where it's gonna go, okay? How do you get this, can anybody you give me an idea about how you can actually get this path and what this path represents, what are the possible paths of the hurricanes? Any ideas? How you can get it? It's very simple, actually.
Least energy?
What was that?
The path in which it takes least energy to come?
Yeah, so how do they come up with this banana? Okay, so you have a numerical weather prediction model, and if you feed it some initial conditions, it will give you, it's a deterministic model, it will give you a path. It will give you a definite path for the hurricane. Right? But here you see basically an ensemble of paths. How do you come up with that?
Be based on the paths of previous hurricanes?
That would be one idea, but that would be statistics. It would not be physics plus data. Another idea? Yes. Where does the error come from?
From previous data, like heuristics.
Okay, maybe. Let me give you one idea. So you have uncertainty in your initial conditions. You have a definite weather prediction model. It's a deterministic model. It's partial differential equations. The only thing that you don't know is how to start it. You can measure the temperature at some weather stations, but in between you're going to have to interpolate. So in between you're going to have to guess what the temperature is. You have a weather station in Lafayette and weather station in Indianapolis, you're going to have to guess what happens in between in order to start your numerical weather prediction model. Well, what you do is you guess many times, all right, and you guess once and you get a path. You guess again and you get another path. And you guess 1,000 times and you get 1,000 paths. And then you say, okay, that's what could happen. I'm not really sure what's going to happen because, how can I guess the initial conditions perfectly? And that's how you get this. So if you look at this, is basically, sampling an initial condition and getting a path, sampling another initial condition and getting a path, sampling another initial condition and getting a path, and then doing that as many times as we can afford in like 2 hours, right? Because that's how fast we need to be able to predict. And then we say, well, we don't. I mean, if you look at CNN, if you watch CNN during a hurricane, you'll see the paths. Okay, and that's exactly what they do. They sample the initial conditions and they pass them through the numerical weather prediction process, the numerical weather prediction models, and they show you the path. And as a matter of fact, they also sample different models because we're also uncertain about the models. So you see the American model, the European model, the whatever model. All right. Now, what are the kinds of uncertainty? The 2 names for uncertain things that people have come up with. There's one type of uncertain variables which we call aleatory, and these are uncertain variables that are kind of naturally occurring and they are irreducible. They correspond to something that is truly random. Uncontrollable, completely beyond your control. It's not like you can do something and measure it a little bit better. It's completely random. It's debatable whether or not they exist. Okay, but you can think of them. And this is one type of uncertainty, aleatory uncertainty. There is another kind of uncertainty which is called epistemic uncertainty, which is uncertainty due to lack of knowledge. So it's basically because you don't really know. You have a variable that has a definite value, but you don't really know it. You don't know it because you haven't measured it yet, or because you can't measure it accurately. You don't have the apparatus to measure it accurately, or because somebody hides it from you, or because it's very expensive to measure it. Okay, any of these things. So remember aleatory and epistemic. Let's see some examples of these variables. All right, so imagine that you have the microstructure. You have here a bevel gear, basically. And this is made out of a microstructure. It could be some kind of steel. Okay. And if you take a point of that gear and you zoom in, you're going to see a specific structure for the material. Okay. Now, would you say that this structure is random? Would you say that we don't really know what it is because you have to look at it, right? So let's say you look at it. Would you say that it is aleatory uncertainty or epistemic uncertainty? Yes? Aleatory? Okay, so true randomness, right? So you look at it and you see this picture. What's going to happen if you look at the same point again? Are you going to see the same picture or a different picture? You have the same gear. You look at, you cut it and you put it in an electron microscope and you look at it and you see a picture. What is going to happen if you look at it again?
Orientation might change, but still
Or if you look at exactly the same, you do the same experiment twice, you're going to get the same. So the microstructure of the gear is something that is actually fixed. Okay, it may evolve slowly in time, but let's say for or the order of a day, it doesn't change, right? So it is something actually completely deterministic. Okay, right now, if you take it and look at it, it's completely deterministic, but you just don't know what it is. And if you measure it twice, you're going to find the same thing. It doesn't change. What may change if you have another gear produced from the same manufacturing process at a different time, it may give you a slightly different microstructure. So for a given, let's say, artifact, a specific bevel gear, that has a specific microstructure that you don't know. Therefore, the uncertainty of that your uncertainty about that microstructure is kind of epistemic. But if you consider the process that produces the gears, that may be something that you would like to, something that may look like aleatory uncertainty when you consider the production of different gears. But if you think a little bit closely, a little bit more carefully, is your manufacturing process something that is truly random? Maybe this uncertainty, this aleatory uncertainty is basically because you cannot perfectly control, let's say, the operating temperature or the material that you put inside your manufacturing process. So even something that may look aleatory, like, spitting out bevel gears out of a manufacturing process, may be actually epistemic just because you cannot perfectly control your manufacturing process. Anyway, I should not talk too much about that because at some point it becomes philosophical. Okay. Here's another example, the example of the permeability. I mean, this is arguably, if you take a piece of ground, it has a very specific form. Again, on that specific time scale, right? It's fixed. It's not random. Kind of looks like randomly arranged, but it's not random. You don't know what it is, so your uncertainty is epistemic. Okay? Here's another example of basically an uncertainty on a physical law. So you have here let's say a model for the dynamics of a protein, and you have the Boltzmann distribution of statistical mechanics, right? So you have there the Boltzmann constant, temperature, and this guy over there is the empirical potential. Q are the degrees of freedom. So that empirical potential, in theory, you can get it from quantum mechanics. In practice, you cannot really know exactly what it is. Okay? And you are uncertain about that. And what you typically do is you say it's gonna be pairwise interactions plus some complicated terms, and I'm going to parameterize it and fit it to some data. And at the end of the day, you cannot really be sure about what it is. So if you want to predict, let's say, how these two proteins interact, you're not going to be able to get it exactly. Okay, you're going to have some uncertainty because of your uncertainty in the model. Okay, so this is another type of uncertainty that we have, which is, let's say, model uncertainty. Is this epistemic or aleatory? It's clearly epistemic, right? Because there's supposed to be some empirical, some potential function that is right, we just don't know what it is. Okay, here's another example. Cosmic microwave background radiation. If you open one of the old TVs, you're gonna see it. Looks, it's the closest thing to aleatory uncertainty that I could find. It looks very random, okay? But again, it kind of looks, it is aleatory. Let's say for all purposes, it is aleatory. But if you really think about it, go back to the Big Bang and think about the initial conditions, then maybe you could predict what it is. Okay, so maybe it's epistemic. Alright, so this is another example of aleatory uncertainty. It is also debatable whether or not it's true aleatory uncertainty or there's something missing from the theory. So if you throw an electron through a screen and you have two slits, the electron may go through one or the other. Okay, and it kind of goes through both because you have interference patterns on the back of the screen. And quantum mechanics, as a matter of fact, does not predict where it's gonna go. It just tells you the probability of where it's gonna go. Right? So, is this epistemic or aleatory uncertainty? So is nature truly random at, the microcosm? Or is it lack of knowledge? Some people would say that it's actually just random, okay? Forget about it. And that's actually the acceptable, let's say, interpretation of modern physics, is that it is actually random, okay? But some people may say, you know what, you haven't really found the right theory. It's not random, it's just that quantum mechanics describes your state of knowledge about something that you don't really observe. And, if you work for 500 years on high energy physics, you may actually find it. All right? So what about turbulence? This comes out you can write down the Navier-Stokes equations, they're deterministic equations. Okay, and they do whatever. Depending on the discretization size of you're gonna have to take your fluid and discretize its description, and that discretization is always gonna be finite. And it is this discretization error that gives rise to what is numerical, let's say, at least turbulence. Okay, so I don't know. If you could represent, instead of, trying to approximate your fluid using a continuum description, if you could just track the position of each one of the molecules of your fluid and do, let's say, molecular dynamics, maybe you could, capture what happens perfectly. But this is not something that we can do. So, and some people will say again that turbulence is aleatory. Some people would say that it's epistemic. If you could have a infinitely small discretization grid, it would disappear. You would actually be able to predict everything. It would be very sensitive to the initial conditions, right? But you could predict, if you knew the initial conditions with infinite accuracy, what happens. But anyway, at the end of the day, it doesn't matter. Okay? It doesn't matter because it's not productive to argue about these things. Whether something is aleatory or epistemic. It's basically philosophical. And the amazing thing is that no matter what an uncertain thing is, there are also, because before I move here, there are also completely different kinds of uncertainties about which we're going to talk later. Okay, uncertainty is about things that you don't even know that you don't know. But let's not get there, okay? But anyway, if you know that there is some variable and you don't know what it is, and that may be because it's truly random or because you just haven't measured it yet or you cannot measure it, the great thing is that you can describe this uncertainty with probability theory. So we're going to be able to say things like, what is the probability that something A, like a logical proposition, is true given everything that we know so far, and that everything that we know so far includes all the physical knowledge that we have derived over hundreds of years of experimentation and thinking, plus any data that we might have. Okay, so this is what K means, everything. And that's a great thing. And originally, the first person who thought like that was actually Laplace. And he thought like that to calibrate his astronomical models. So he had missing parameters, and he had observations of the planets, and he had to calibrate these missing parameters. And he said, well, I don't know what they are. Therefore, let me just put a probability distribution on them and treat them as uncertain in this way. And he basically invented probability in the way that we're going to talk about right now. And this is a very good book that takes this point of view. And I suggest that you read at least the first chapter. Okay? It becomes a little bit this is great, but don't take everything that E.T. James says for granted, okay? Because he's too harsh on the other guys that think of probability differently. So let's be a little bit, let's take a more moderate view. But this is the guy behind the maximum entropy principle and the formulation of statistical mechanics using the maximum entropy principle. So he's a serious person, okay? Right, so what we're going to be doing is we're going to be coming up with things like that, like the probability of getting a given microstructure, given all the knowledge we want. And this looks, it is as complicated as it looks, right? So here you see this is the standard, let's say, uncertainty quantification problem. It's a density estimation problem. How do you get this, right? So maybe you can measure different microstructures many times, and you need to come up with the generating distributions of this microstructure. Maybe you measure the same bevel gear at different points. But it's a density estimation problem nevertheless. And what you see here is that this object that goes in there is high dimensional. It's clearly high dimensional. You need a lot of degrees of freedom to describe what it is. So that's why this is difficult. All right. Yes. No, this is going to be, this uncertainty quantification problem, right? So this is going to be what is your input to whatever analysis you do later. Like, for example, how can I construct a bevel gear that is robust to something, to manufacturing variations, right? So what you really want is a generating distribution that gives you microstructures that look like the real deal. Cannot really predict exactly what it's going to be, right? But it has to be representative of what goes on. So I think I'm going too slowly, so let's just spend 5 minutes on this exercise. Let's get started. Turn on your computers. Okay, so even if we don't have time to go over this in class, and we may not have, you can actually do it offline, okay? So don't worry about it. What I want to point out is that you're supposed to read this, okay? And then you're supposed to run each one of the code blocks, okay? Hopefully this is how you're gonna catch up with Python and Jupyter Notebooks, and that's all the reading you're gonna have to do for Python. But let me just go through this example first and then let you guys work on the questions for a little bit. So here I just load the data. I have data from a catalysis experiment that is supposed to produce, what does it produce? A nitrous oxide, I think. And here you have measurements of the reactor at different times. And here you see the concentration of each one of the species. And if you sum up the masses, they should be conserved. But these masses are not conserved because there is an unobserved species. Okay, so this is how the evolution of the process looks like. And we're gonna come up, so this guy, Katsunaros, which is one of my collaborators, I mean, he summed the masses at each at each time, and he saw that there's something missing, so he postulated that there is an unobserved species that accounts for this missing mass, and he came up with a dynamical model that looks like that. So I tell you that this species turns to this species with a specific unknown rate, and then this to that, and this to that, and this goes to the unknown species with an unknown rate, and then this goes to N2. Okay? Now all these reaction coefficients are parameters that we are uncertain about, and we want to infer them from the experimental data. Now the physics of the model look like that. This is a dynamical system. So you see here NO3 is decreased with that rate, and then NO2 is basically increased proportionally to NO3, and so on and so forth. Okay, this is a classic kinetic reaction model. Okay, this is a dynamical system, and we do not know these parameters. Okay, K1, K2, K3, K4, and K5. The rates at which the different species turn to other species. But we do know the initial conditions because this guy measured them, okay, accurately. So I would like you to go and click on this link right there, okay, and you're gonna get a survey. The first thing you need to put in the survey, and this is the only mandatory thing to put in the survey, is your name, okay, your email. And then you should really just go through the questions. This should be very straightforward to answer. And they don't have a unique answer or a correct answer. Kind of have a correct answer. And you're not supposed to do that on your own. You can talk with the people around you, and I would really like to hear a buzz. Maybe not the first day because you're going to be a little bit shy, but you know, maybe later you can start talking to each other. And then at the very end, hit submit. Okay, that's pretty much it. So let's spend 5 minutes on that. Let's spend the first 30 seconds getting to know the people who are around you, right? So please talk to each other. Introduce yourself. Hi, my name is, etc. Okay? Okay, so let's get back. Please, if you haven't finished, don't hit submit yet. Keep it open, you'll do it later. Okay? We'll have at least one more, you have at least 10 more minutes to work on this. Okay, so let's change gears and let's start talking about the uncertainty propagation problem and what are the challenges. So here's how we're gonna idealize the situation. Okay, so we're always gonna have a physical model on an experiment, and that physical model, of course, is gonna have physics in it. Okay, it's not gonna be a black box all the time. It has some input parameters or control parameters or something that you can change. Perhaps you cannot control them perfectly, or maybe they are completely beyond your control. Okay, but they're nevertheless inputs to the system. And then there are some quantities of interest that you can get out of the system. That is, you can get them either by simulating the model, running it on your computer, or by doing a physical experiment and measuring the response, right? And of course, this can have noise and so on and so forth. Now, here's how we're going to idealize it. And this is not perfect, but it's a start. I'm going to call the inputs X. Okay, common name for inputs. We're going to call the physical model F. Chose F because it's going to be a function. And then the quantity of interest, we're going to call it Y. And we're always going to think of this situation as a function of X that gives you a Y, and X is the input, and F is whatever you're doing, simulation or experiment, and F of X is the result of that, which we're going to call Y. Now, sometimes F of X is going to be a model prediction, and Y is going to be an actual measurement, and this equality is not going to be perfect. Okay, it's going to be kind of like that. But this is how we're going to think about it. Okay, and here's some UQ problems. Okay, here's the uncertainty propagation problem written down in this language. You have a probability distribution on the inputs that corresponds to your state of knowledge about what the inputs are. If this is an experiment, you select the inputs of the experiment, but you have a trembling hand, and you cannot do that perfectly. And then you want to see how this uncertainty is going to go through your model or your experiment and induce uncertainty on your measurement. Okay? We'll see a specific example in the next lecture. We're going to show you how the initial conditions of the coin toss affect the result of the coin toss. And then I'll also tell you how to throw it so that it always comes up whatever you want. Alright, this is the uncertainty propagation problem, so take the uncertainty through the model. The model calibration problem does the opposite thing. You start by a measurement of your quantity of interest, an experimental measurement of your quantity of interest. You say what you think about the input to your model or to your simulation to your experiment before you see any data. And then you ask the question, what should the input be? It doesn't really matter. I don't want you to understand what this means right now. You'll do that eventually. But you have your experimental measurement and you say, what is the input that gave me that experimental measurement? Assuming that my model is right, of course, because your model may be wrong. Okay? So this is the inverse problem or the model calibration problem. And then you have the design optimization problem that looks kind of like that. It is basically to maximize an objective that depends on the result of your simulation averaged over things that you don't know. And these things are excised there. 6 lectures, 3 lectures, 2 lectures, and about 15 lectures to explain the language. Okay? So we're not rushing. Now let's concentrate on that for the time being. Let's not do that now. You do it eventually all at the end because it will take a while. So in this hands-on exercise, I ask you to just calibrate the model by hand. So I give you bars that control the parameters of the model. And you just have to move the parameters around until you visually match the experimental measurements. Okay? This is the intuition way of doing it. You do that. You'll do that in a while. But for now, let's talk about two other ways of doing it. Okay, that are a little bit more systematic. Okay, this will give you the opportunity to write a little bit. So pick up a pen and start writing. All right. So what is the natural way to calibrate a model? So let me just first write a few things. So let's say that your model is f of x. Okay? X is the parameter you're looking for. And let's say that you observe y hat. Okay, so you do an experiment and you measure y hat. So how can you find x so that f of x comes as close as possible to y hat? And you pose a mathematical problem instead of just, trying out different x's until you find the match. Any ideas? I mean, the experimentalists who are 50% should be able to tell us. Or Alana, yes? You can do a regression between x and y, but you don't measure x. You don't measure x. X is what you're looking for. You just measure y. Right? What was that? You do know f of x. So let me give you an example. You have an apple and you let it go and you measure how much time it takes to hit the ground. You know the height, you measure the time, and you want to find the mass. Okay? You want to find the mass. So the unknown parameter x is the mass. And you do this once, by the way. Okay? And you know everything except the mass. So everything else, the time it takes to go down and the height is inside f. Okay? And you just want to find the mass based on the measurement. This is fairly simple because this is going to be a quadratic function, a linear function of the mass. So you can just say the mass is this divided by that, okay? For this example. But imagine an example where you actually have to solve a finite element problem to get the prediction of your model. And it's not something that is analytically given to you, right? So even though f of x is known, it's not like a simple function, okay? It's kind of like a black box. So what will you do? Yes?
Explore the parameter space.
Okay, so that's one, this is a very good idea, and that's actually what you are going to have to do in your handout, right? So you say, here's x, here's what I actually measure, y hat, right? So I'm just going to be moving trying all the x's that I can, right, until I find this one. Yeah, that's totally fine. You can do that. But, no, you can do that. But let's say that x has 20 dimensions. Okay? Or 5. Then you're gonna do it. I mean, you can still do it, but you're always gonna look at slices, right? So is there a more systematic way of doing it? Any idea? Okay, now I understand why 37% said intuition for calibrating problems. Okay, here's a very simple way, right? So you say, I'm going to define a loss function, a function that tells me how close the prediction of my model is to what I measure. That's a very simple loss function that you can come up with is f of x minus y hat squared, because you don't really care about the difference, right? So the smallest this value, the better f of x matches y hat. Yes?
Isn't that kind of regression?
No. It is a regression if f of x is a linear function of x. Then it's the same problem. But if f of x is a complicated physical model and x are the parameters of that model, Like, for example, a partial differential equation could be what f is, and x could be the initial conditions. Then you know I'm not going to have a linear relationship between the two. So f of x is any physical model you like. So you define this loss function that tells you how close the model prediction is to your experimental measurement, and then you say, well, I want to minimize that loss. Okay? So you say, you pose a mathematical problem, you say, so you turn it into an optimization problem. That is, minimize L of x over the possible x's. Okay? So this thing now is a nice mathematical problem that you can, let's say, use Python to solve. Okay? Without really doing anything by hand. All you have to say is what your model is, what your loss function is, and what is the set of parameters that you want to consider, and then you can just run an optimization algorithm, like, for example, random search, gradient descent, conjugate gradients, BFGS, Newton-Raphson. We'll spend a lecture just on this problem, okay? So lecture 20 is going to be on this problem. But let me show you now some issues with this problem. So here, let me use this picture right here to show you what the issues could be. So one of the issues that you could have is that your model may actually not match the data for any x. This is actually what is going to happen. I can guarantee that. Okay? So you may not match it because of uncontrollable parameters kicking your observations, or because you just have the wrong model. Okay? Another thing that can happen is that your model matches the data for two x's, for this one and that one. And which one of the two is right? This can also happen if you don't have the right model. Okay? Or the other thing that can happen is you can have another model that matches the data and it's as good as your own model. Then which one would you choose? This is the third problem that can happen. Okay? So we'll spend a lecture just on that. Any questions? Yes.
So how do we make sure we reach a global minima here? What is,
For this one?
yeah.
So this is what we're going to be talking about when we talk about this problem in lecture 20. So if you use, for example, a standard optimization method. So who has taken here a course on optimization methods, numerical things? Okay. So you know that all the numerical algorithms will converge to a local minimum that depends on where you started. Right? So what you do is you start at many different places many times, and then you get the smallest. Okay? Of course, there's no guarantee that this is going to be the global minimum, but it's going to be better than just trying out one. Okay? All right. There's a more natural way to calibrate the model, and that's the Bayesian way. We're not going to talk about that. Okay? Because there's no time. I have planned for it, but no. Okay? It's going to be lecture 21, but it's really going to need at least 7 lectures to be able to actually do it. To do it in reality. So this way, the Bayesian way, will basically, we will be able to deal with all the difficulties. So what if the model cannot predict the truth? What if you have 2 models that predict the truth? What is the observation? What if you have 2 model parameters that give you the same prediction? It will deal with all that. Okay? And on top of that, it will also give you uncertainty about your model parameters. It will tell you, you know what, you should not be really sure about X. This is the uncertainty you should assign to it. So it will give you this. And it will also be able to give you an answer to the following question. What is the best experiment that you can do if you want to determine X as accurately as possible? It will also be able to tell you this and to help you formulate this as a mathematical problem. Okay. Now, I will skip that as well, because I want to give you at least 10 minutes to work on the handout. So it's okay, I will skip all that because I will actually talk about them when we talk about Monte Carlo. So let's just spend the next 9 minutes on the rest of the handout up to question 3, which we should be able to answer without any of the presentation slides.